The modern digital economy is hitting a physical wall, most visible inside AI compute clusters. These systems are frequently throttled by tail latency and jitter, issues that leave expensive GPUs sitting idle while they wait for data to arrive. We see the same scaling crisis in 5G telecommunications, where network slicing and automation are bottlenecked by these same coordination limits. The underlying problem is that legacy networks cannot securely or predictably route the high-dimensional traffic these modern workloads generate. Tensor Networks Inc. claims to solve this with a tensor geometric control architecture, a system that manages the network as a compressed, forecastable geometry. For a deep tech investor, this raises a difficult question. Is this a brilliant physics experiment, or is it a deployable, revenue-generating enterprise platform? The investment opportunity is a conditional yes, but only if you strip away the physics metaphors and evaluate the software on its operational merits alone. This table helps clarify the investment by splitting the company's pitch into two distinct components. On one side is TNQG, Tensor-Network Quantum Gravity. This is a conjectural physics framework. It is research, not a product. On the other side is PTCP, the Predictive Tensor Control Plane. This is the actual software, a risk-aware AI ops overlay designed for high-dimensional telemetry. TNQG has value as a branding and recruiting tool for elite math talent, but it will not drive near-term revenue. If capital is diverted into proving quantum gravity instead of validating this software, the startup faces extreme execution and regulatory risks. Your due diligence should focus strictly on the PTCP software. The physics research should not absorb your product capital. This diagram represents the core technical claim. PTCP ingests multimodal telemetry, like link utilization, queue depth, trust scores, and energy costs, and collapses it into a tensor train format. The intended outcome is a drastically reduced storage footprint for complex network states. However, this mathematical compression relies on strict rank assumptions. Improper tuning could cause the system to discard rare but critical tail latency events. Overcompression could also miss the subtle, low-frequency precursors of a sophisticated security breach. The math is elegant, but it remains a liability until benchmarks prove it preserves these anomalies in live traffic. To make these insights actionable, PTCP employs a method called bounded actuation. This approach guarantees that automated routing decisions never break network reachability. It also ensures zero-trust security policies are structurally maintained during dynamic path changes. These rigid safety boundaries mathematically limit the maximum efficiency the system could theoretically achieve. Network operators will aggressively block any AI controller that causes unpredictable outages. Even a perfect optimization engine is useless if operations teams do not trust it enough to grant it production control. On the security front, PTCP treats anomalies and identity shifts as geometric topology defects. This integrates zero-trust posture directly into routing decisions, rather than treating security as a separate dashboard alert. But positioning the product as a core security tool puts the company on a collision course with the SASE market. Massive incumbents already own the enterprise security budgets and the established security operations channels. Tensor Networks must enter as an augmenting partner, rather than attempting a total replacement. Competing head-on for existing security budgets will likely exhaust their runway before they can prove their routing superiority. This reality leads to their primary strategy, operating strictly as a vendor-neutral overlay software. This allows integration with hardware from Cisco, Arista, and NVIDIA without requiring a disruptive rip-and-replace of existing infrastructure. However, overlays add computational overhead, and they are vulnerable to incumbents who might bundle similar features for free. This bar chart outlines the capital allocation required to manage that risk. The majority of funding must go toward building standard APIs and reducing controller overhead. Exploratory research should be financially restricted until the core product is validated by customers. Flawless integration is the only way to prevent hardware vendors from blocking adoption. This flowchart maps out the final strategy for investors: ruthless, milestone-based capital gating. Capital should only advance if baseline benchmarks and latency reductions are proven in reproducible trace replays. If you are looking for a quick SaaS flip, or if you lack the technical capacity to conduct independent benchmarks, this is not the right investment. But it is worth pursuing for corporate innovators with telemetry access or VCs capable of enforcing strict technical due diligence. The most effective wedge to begin these proofs is inside AI data centers, where the financial cost of latency is highest. The final verdict? If PTCP delivers reproducible results across the multi-billion-dollar markets for SDN and Zero Trust, the company becomes a category-defining software asset. But that outcome requires a benchmarkable operational artifact.